Okay, so today we're going to be talking about a special type of motion, and this is motion with constant acceleration. So constant acceleration is just saying that the acceleration is not changing. It will remain at the same rate throughout the whole problem. Okay, so we're going to come up with some equations that we're going to use. Now all I'm going to be doing is deriving or showing you where these equations come from. It's not important that you understand and rewrite how these equations are coming, but I will tell you which the equations are at the end, and those are the ones that we're going to be working with. Okay, so we're going to start with the definition of acceleration, and we found this from last video. The average acceleration is just the change in velocity over the change in time. So if I take this equation and I do a quick cross multiplication here, and I multiply the time by the average acceleration, I'm going to have an average acceleration times the change in time is equal to the change in velocity. Well, remember from the other sections that the change in velocity is just the final velocity minus the initial velocity. So right here we have the final minus the initial. Now what we're going to do is we're going to do some general algebra. We're going to add the initial velocity to both sides of the equation. So here we have negative v initial plus v initial, and that ends up being 0. So what's left is the v final down here. And over here we're going to say v initial here plus average acceleration times time. So what we have here is that when we have constant acceleration, the average acceleration is the acceleration. So for instance, what is the average of the number 5? Well, you only have one number, therefore the average is 5 divided by 1, which is 5. So we have the same thing here. The average acceleration is just that acceleration that's constant divided by 1, which is equal to acceleration. So we're going to get rid of this subscript average, and we're just going to say that it equals at A, the acceleration. So I'm going to rewrite this equation right here. I'm going to start with the v final over here. It's going to equal v initial plus, instead of A average, we're just going to say A. Instead of delta t, we're going to assume that the final, the initial velocity is 0, so we're just going to say t. This is our first equation of motion with constant acceleration. We know that the final velocity is equal to the initial velocity plus the acceleration times the time. Okay, so we're going to try working an example first. Okay, so our first example, we have a plane starting at rest at one end of a runway. It undergoes a uniform acceleration of 4.8 meters per second for 15 seconds before it takes off. What is its speed at takeoff? Well, what we're going to do in physics is we have word problems, but we're going to have to decipher what is important information and what is just part of the sentence. So we're going to start here, a plane starting at rest. So the fact that it's starting at rest is telling us the initial velocity is at rest. At rest means 0 meters per second. So our initial velocity is 0. Then we're going to look at one end of a runway undergoes a uniform acceleration. Right here, the word uniform acceleration is the same as a constant acceleration. It's not changing. So we know, because of this word uniform acceleration or the word constant acceleration, we know we can use the equation that we just derived. So we know that acceleration is 4.8 meters per second squared for 15 seconds, that's our time, before takeoff. What is its speed at takeoff? Well, we're looking for the velocity when it goes right before it takes off. So we have a plane that's starting at 0, it's going to be accelerating constantly until it's fast enough, the velocity is large enough, and that's what we're looking for it to take off into the air. So we're looking for the final velocity. Our unknown is v final. So we're going to start with our kinematic equation. Velocity final equals velocity initial plus at. And in this case, we're just going to plug in what we have. Our initial velocity is 0. Our acceleration is 4.8, and our time is 15 seconds. And right here, you can look at what we're going to do. We have two s squared on the bottom and s on the top. So this is going to go away, and this is going to go away, and we're going to be left with meters per second. And then we can double check. That is the SI units for velocity. So we are dimensionally correct. So if we plug this number into our calculator, 4.8 times 15, we end up with 72 meters per second. So this airplane starts at 0, it's not moving, it gets faster and faster and faster for 15 seconds, and it finally reaches 72 meters per second, then it's fast enough it's going to start taking off. Okay, so we have more than one equation that we're going to be using for these motion with constant acceleration. The other one we're going to do, and once again I'm going to show you how I'm going to derive it, but what's really important is the equation itself. Okay, so we're going to start with this equation. The average velocity is change in x over change in t. We also know the average of any two numbers is the numbers added together divided by 2. So we're going to add the initial plus the final and divide it by 2. That's another definition of the average velocity. So now I'm going to take these two middle equations. If I know the average velocity equals this, and I know that this equals the average velocity, then I can make the assumption that these two equal each other. So I'm going to take this equation down here, this one down here, and I'm going to set them equal to each other, and I'm going to start solving. So I'm going to do cross multiplication. I'm going to take the 2 times the delta x. So we have a 2 over here, and then I'm going to times the delta t times v1 plus vf times delta t. Okay? Then what I'm going to do is I'm going to divide the whole equation by 2. Or, in other words, I'm going to multiply by 1/2. Well, these 2's will cancel out, and we're left with delta x. This 1/2, now this would be over the whole equation, is the 1/2 v1 plus vf times delta t. Well, from the first equation that we had, which was vf equals v initial plus at, I'm going to take this whole equation right here and I'm going to plug it in where we have v final. We know that v final equals that, so I can replace it. So now I'm going to have delta x equals 1/2 v1 plus, now the vf, I'm going to put v1 plus at here times t. And once again, we're going to make the assumption that we're starting at 0, so our delta t equals t. If I clean this up a little bit, I have v1 and v1, which equals 2v1, times 1/2 is just v1. And then the 1/2 at squared is right here. So this ends up being our second kinematic equation, or our second equation of constant acceleration. Our delta x, or our displacement, is equal to our initial velocity plus 1/2 a t squared. That is our second equation. So let's try an example using those equations. Okay, example 2. We have an automobile with an initial speed of 4.30 meters per second. It accelerates constantly, that's that word, accelerating constantly, at a rate of 3 meters per second squared. Find the final velocity, so we're looking for v final, and the displacement. We're also looking for delta x after 5 seconds. So if we take this word problem and we break it apart and get out what we need out of it, our given is that its initial velocity is 4.3 meters per second. It says an automobile with an initial speed of 4.30 meters per second. In this case, our velocity and our speed are the same. They're both going in the same direction. So our initial velocity is 4.30 meters per second. Now it says it accelerates constantly, which is the same as accelerating uniformly, or constant acceleration, at a rate of 3 meters per second squared. That is our acceleration. And it says that it does this after 5 seconds, so our t is 5 seconds. Our unknown is our final velocity. It says find the final velocity, and the displacement, which is delta x. So in this case, we're going to do 2 separate problems. Our first one, we're going to start here, and we're going to say that our final velocity, this is our first kinematic equation, our final velocity equals initial plus at. Well, I'm looking for my final velocity. So my initial velocity is 4.30 from right up here, plus a, which is from right up here, times t, which is a given. So if I plug it right into my calculator, I know that my final velocity is 19.3 meters per second. So that's our final velocity. They're also asking us to find its displacement. So now we're going to use the second kinematic equation that I gave you, and I know that my displacement is equal to my initial velocity times my time plus 1/2 a t squared. So I'm just going to plug in all our known. Initial velocity 4.3, time is 5, 1/2 stays 1/2, a is 3, and t is 5, and that's 5 squared. If we plug it into our calculator, we end up with our displacement is 59 meters. So this means that this car, starting at 4.3 meters per second, is getting faster and faster. For 5 seconds, it's gone 59 meters. And the velocity at that 59 meters is 19.3 meters per second. Okay, here's another example, and we're going to work this one together. Okay, a car starts from rest and travels for 5 seconds. with a constant acceleration of negative 1.5 meters per second squared. What is the final velocity of the car? Also, how far does the car travel in the time interval? So let's set this up, and then I'm going to have you pause the video and try to solve the problem and then come back. So we have a car starting from rest. That is telling us that our initial velocity is 0. It travels for 5 seconds, time is 5 seconds, with a constant acceleration. Once again, this is the key word, constant acceleration. That means we may use these equations of negative 1.5 meters per second squared. So our acceleration is negative. It's important for that negative. Remember from the previous lesson, what does a negative acceleration mean? Well, it can mean many things, but because we're choosing that this car is moving in a positive x direction, we know that the negative is telling us that it's slowing down. So we know that this car is going to be getting slower and slower and slower. Okay, so with a constant acceleration in it, what is its final velocity of the car, and how far does this car travel in the time interval? Okay, so we're looking for v final and our delta x. Okay, so what I want you to do now is pause the video and then come back and we'll solve it together. Okay, so I'm going to be using the first kinematic equation. V final equals V initial. It's a VI plus AT. We're looking for V final, so we know V initial is 0 plus A. In this case, it's negative 1.5 meters per second squared times T, which is 5 seconds. Okay, and just verifying that we are dimensionally correct. This seconds will cancel out. We'll end up with meters per second, which is the correct units for velocity. So if I plug this number into my calculator, my final velocity is negative 7.5 meters per second. Well, what is this negative telling us? Negative is telling us that it's now moving in the opposite direction, which kind of makes sense. If we're starting from 0 and we're accelerating at a negative 1.5, we have to be moving in the opposite direction. Otherwise, our velocity would be increasing. Okay, so we have our final velocity is 7.5 meters per second. Now, the second part of the question is asking us how far does this car travel? How far is another word for displacement. So we're going to use the second equation, delta x equals V naught t. I'm sorry, that's V initial. In the AP, we use the word naught, but it's V initial t plus 1/2 AT squared. Okay? So let's plug our numbers in. We know our initial velocity is 0. We know our t is 5 seconds. And this, luckily, is going to go to 0 altogether. Plus 1/2 A. A is negative 1.5 meters per second squared. And t is 5 seconds. And this is squared. So if I plug this into my calculator, this whole thing goes away. We end up with 1/2 times negative 1.5 times 5 squared, which is 25, and we end up with a displacement of negative 18.75 meters. Once again, that helps us. This negative is telling us we're going to be displaced, or our motion is going to be in that way, which corresponds with the negative velocity over here. Okay, so for a quick overview of what we learned, we have 2 equations that I verified for you. These are equations of motion with constant acceleration. This was the first one, this was the second one, and then right here is our third one. The derivation for this one is a little bit more confusing, so I'm going to leave it up to you to look in your textbook if you want it. Otherwise, we just know that our final velocity squared is equal to our initial velocity squared plus 2 times acceleration times the displacement. Okay, so don't forget that you have an Edline assignment to finish for tomorrow. It's going to be Edline assignment 17. And then tomorrow we're going to work on a whole bunch of these problems. So bring any of your questions to class with you tomorrow. Otherwise, we'll see you, and happy problem solving.